Lab 3, Black Hole and Orbits. Introduction. So the purpose of this lab in part 1 was to analyze the motion and forces acting upon a star to determine the mass of a black hole. And at part 2, we aimed to simulate the motion and forces acting in a system that included a planet, moon, and a spaceship. The overall purpose was to observe orbital motion as it is affected by gravity. A brief glimpse into our findings was that the mass of the black hole was 9.22 times 10 to the 33 kilograms, and the initial velocity of the spaceship was 24,400 meters per second in both the x and y direction. The fundamental physics concepts we used was Newton's second law, which relates momentum and force, and we can see in the bottom left equation it relating momentum to both its parallel and perpendicular components. We also used the gravitational force to determine the mass of a black hole. You can see the bottom right equation is just a rewritten version of the top one, where we have that the mass of the black hole is equal to the change in momentum of the star times the distance between the star and the black hole squared over the gravitational constant and the mass of the star. In part 1, our system was the star and our surroundings was the black hole in space. We used a seed, as you can see in the top right, which is just our email to make sure all of our results is unique to the person finding the calculations. And you see our initial conditions with the mass of the star and the time interval between imported data points up at the top right. And to find the mass of the black hole, we took this calculation loop, which basically calculated the mass of the black hole at different times as the star was traveling around it. You can see on the left here, we started with the initial and final velocity and multiplied that times the mass of the star to find the initial and final momentum, which we then converted to find the change in velocity and change in momentum. Found the change in momentum over time, which is equivalent to the net force, and then we could find the parallel and perpendicular components of both the force and the momentum. Next, we finally could find the mass of the black hole at that point, which looks almost identical to the original fundamental physics formula from the beginning. After running the code, we can see the path of the star as outlined in the picture on the left, about 3/4 of the way through its revolution. We can see the force parallel, perpendicular, and the net force acting on the star in this position. The parallel force being the purple arrow, the cyan arrow being the perpendicular force, and the orange arrow being the net force acting on the star. In the graph on the right, we can see the plotted values of all the masses at each time interval. Averaging them up, we can find that the average mass of the black hole is that 9.22 times 10 to the 33 power. In part 2, our system included the moon and the spaceship, and our surroundings were the planet and space. In this part, we calculated the net force on the moon and the net force on the ship by relating their positions, masses, and force of gravity on each other. Once we found the net forces acting on the moon and the spaceship, we updated their position and velocity, as seen in the top right here, to determine their path as they orbited each other and the planet. The aim of this was to create a computational model that could take in initial velocities of the spaceship and determine whether or not the spaceship would crash with the planet or the moon. These were the results we found for a trial run that did not crash into either the planet or the moon. You can see at the bottom there the path of the starship and the moon, with the path of the moon being in the cyan color and the path of the starship being in the purple color, with the planet at the origin in blue. The initial conditions that we found is at the top right there. In part 1, we can see the difference in the net forces and change in momentum with how they are calculated. Mathematically, they seem the same. However, to find the net force, you need to know the sum of all forces, all external forces acting on an object. Whereas to find the change in momentum, you just need to know the change in velocity of that object and multiply it by its mass. Now in part 2, what if we had included the black hole in our system? This would force us to include the gravitation of the black hole in each of our calculations. This means that the net force acting on the ship, the planet, and the moon will all now also include the black hole.